Hey guys, Mr. T here. This is a video on feasible regions. So this is the first sort of tricky topic that we're going to encounter this year in Year 12 General Maths. It's sort of an extension on linear relationships that we have done in previous years. Now the idea of linear programming is it's a method of solving problems that involve linear relationships, but where the linear relationships are involving and using up the same sort of limited resources. So previously, all we've considered a linear relationship to be is something involving two variables, generally x and y. But now we're considering when those linear relationships are limited by x and y having some form of limitation to them. Either they have to add up to a certain amount, or there's only a certain amount of them available. So linear relationships have so far been assumed to continue infinitely because we haven't worried about any limitations. But obviously in real life there's always going to be limitations on resources. The limitations are also known as constraints, and we'll call them constraints for the purposes of this topic. These constraints define the set of all possible solutions for the problem when we're considering the limits that are imposed by those constraints. So they're known as the feasible solutions. So previously we had one solution for two linear relationships simultaneously. Now we're setting limitations for these. There can be multiple solutions, but they're within a certain range defined by the constraints, and they're known as feasible solutions. So to clear all this up, because right now it's just words, let's have a look at this example here. Jason and Kate are running a barbecue. They can purchase sausages for 40 cents each and steaks for $1 each. Jason and Kate have only $20 to spend. So, like previously, you've had dollar amount relationships before. The only extra here is that we have a limitation, and obviously that limitation is going to affect how many sausages and steaks we can buy overall. So let's break that down. From this question, we can conclude that the total number of sausages, the total cost of sausages is going to be, if we were say number of sausages was x, it would be 0.4 times by x, because it's 40 cents each, so $0.4 times by however many sausages were being bought. So I'm going to just say here x is number of sausages. So you can see that expression there, 0.4x, would represent the total cost of sausages in their purchase. What about the total cost of steaks? Well, $1 each, so that instead of being 0.4, that would literally be 1 times by the number of steaks, and we'll call the number of steaks y, and 1 times by a variable will just be that variable, where y is number of steaks. Make me hungry just think about this. Alright, constraint limitation. Now we have to think about what the limitation or the constraint entails. It's saying that they have only $20 to spend. So the constraint limitation is telling us total spend must be $20 or less if they're allowed to spend less than that. Right now we haven't dealt with whether they're allowed to spend less than that. It's probably a given because they only have $20. They can spend a bit less than that, but we'll deal with that as if they had to spend exactly $20 for now. So what's the relationship linking the variables and the constraint? Well, if the total cost of sausages is 0.4x and the total cost of steaks is y, well, the total cost of everything is going to be 0.4x plus y. And then after that, now that we know what expression represents the total cost of everything we can relate it back to the constraint by saying that the total cost of everything, 0.4x plus y, must be $20. So we have a little equation here that links our variables with the constraint defined in the question. Now, you can certainly come up with some of the possible solutions to this. This is an equation, okay? We could come up with solutions that equal 20 by using trial and error, or by having a look at the extremes. So I'm not going to show a trial and error example here, that would take too long, but let's pretend that we were buying no sausages. So in that case, 0.4 and 0 sausages plus y is equal to 20. 0.4 times by 0 is 0, plus y is equal to 20. Therefore, I bought no sausages. 0 sausages. 20 steaks could be bought. Okay? Let's say we're buying no steaks. So these are the extreme possibilities. Okay? If I was buying no steaks, it would be 0.4x plus 0 is equal to 20. 0.4x plus 0, well, that's going to be nothing left over, is 20. And the opposite of timesing something by 0.4 is dividing by 0.4. And so the solution, grab a calculator. 20 divided by 0.4 is 50. So because the sausages are cheaper, we can buy more of them if all of the money was dedicated to buying sausages. Therefore, 50 sausages, 0 steaks. And that's all well and good. The only problem is that this relationship has many different solutions. We could buy certain combinations of steak and sausage to ensure we have a mix, rather than just no sausages and all steaks, or all sausages and no steaks. We don't have time to do a trial and error solution to this. It would take too long to find all possible solutions manually. You'd try one sausage and see what you got, try 2 sausages. It's going to be too many different steps there. So instead, because the relationship involving the 2 variables and the constraint is a linear relationship, have a look. That's a line equation given in general form. Because it's a linear relationship, it can be graphed, and you can see a visual relation, a representation of all possible solutions. So I'm going to write that relationship here. The equation is 0.4x plus y is equal to 20. How do we draw a line from general form? Well, the y-intercept is when x is equal to 0. 0.40 plus y is equal to 20. Y is equal to 20. Your y-intercept is at 20. X-intercept is when y is equal to 0. 0.4x plus 0 is equal to 20. 0.4x equals 20. Get rid of the 0.4 by dividing by 0.4 both sides is equal to 50. You'll notice these extremities are actually those intercepts, are the extremities that we mentioned there. They're possible solutions. These are the extreme possible solutions, which are the x and y intercepts. So I can graph this now, given that information. And apologies if my line is a little wonky. I've got plastic ruler on a plastic screen. So the x-intercept is at x is equal to 50, dot there. Y-intercept is y is equal to 20, dot there. And draw a line with this ruler that's slipping all over the place. That's reasonable. A little bit off. Just something to mention now, while we're early on the topic. Your accurate answers to these particular kind of questions rely on you drawing your graph extremely accurately. So get used to adjusting lines to make sure that they go through points exactly. That's too low. I need to squidge it up a tiny little bit. Hopefully this goes through. Still no good. This has to be my last try. It's not interesting watching a guy struggle to draw a straight line on a plastic screen. But that's the world we've come to. Oh dear. That can't be the last one. Mess it up even more. So I am leaving this in to make sure that you understand that the accuracy is extremely important. I have to leave it at that. Okay, and I'm happy with that. So you can see our 2 points here. X is equal to 50, the y-intercept, y is equal to 20. Those are actually solutions. Because the x-axis is number of sausages. This is one solution, 50 sausages. 0 steaks would result in a total spend of $20 still. Here you have 0 sausages and 20 steaks as represented by the y-axis, number of steaks. Steaks does not have an E. Is another solution of the extreme that would add up to $20 spend. But the key for this is that now we can see the other possible solutions to this question. All of these whole integer crossovers here are possible solutions as well. You can see here that the line drawn crosses exactly over 518, which represents 5 sausages bought, 18 steaks bought, is a feasible solution. It's a possible solution to this. Another point here is 10, 16. You could buy 10 sausages, 16 steaks. Another one here, 15, 14. You could buy 15 sausages and 14 steaks, and so on. All of these whole number crossover points, because we're not considering buying half sausages and half fractional sausages, fractional steaks. All of these are possible solutions. 20, 12, 25, 10. I'll fill this out. 30, 8. So once again, these are feasible solutions if you wanted to spend exactly $20. 35, 6, 40, 4, 45, 2, and the last one was the extreme of buying 50 sausages and no steaks. So at this current point in time, if we were saying you needed to spend exactly $20, these are the feasible solutions going across here. Whole number crossover points there, and the extremes on the x and y intercepts. That's currently the feasible region if we wanted exactly a $20 spend. However, what if you could spend $20 or less? What if there was just a limitation of a maximum of a $20 spend? You didn't mind spending less than $20. Then the relationship would become 0.4x plus y. The total of the cost of the sausages and the cost of the steaks can be less than or equal to $20. We can't exceed $20. In that case, the feasible region is not just on the line. It can be any of these whole number points underneath the line. So I'm going to try to color this in without making it look too bad. This is now the feasible region. Previously, if we were saying exactly equal to 20, the only feasible solutions were exactly on the line. But what if we're saying that we can spend up to $20, but anything less than that, it's good too. All of these solutions underneath are feasible solutions as well. So instead, we have a feasible region. That would be the case if it's less than or equal to. It's underneath the line. If it was greater than or equal to, it would be past the line and nothing underneath. So these solutions here are not feasible. These combinations of sausage and steak outside, above the line, are not feasible. Not feasible solutions. They would be greater than 20, therefore beyond the constraint. The constraint is 20, and you can spend less than that. Any of these other solutions, so for this one, for example, 41 sausages, and 13 steaks, that would be too expensive. However, everything underneath the line in the feasible region would be less than $20, so it's a possible solution. It's just not spending the whole amount. So this would be 20 sausages and 4 steaks. What would the result of that be? Well, that would equal 0.4 lots of 20 plus 4 is equal to $12 spend. That's less than $20. That's perfectly reasonable. If you're just setting the limitation of a maximum 20, you're happy with anything less. So all this stuff underneath the line are feasible solutions. Therefore, we have what's called a feasible region of possible solutions, which is shaded in. Okay, so hopefully that's a little taster, a little introduction to the idea of feasible regions and how they're constructed and what they represent. They represent possible solutions that aren't exactly equal to the constraint. Alright, hopefully that's shown you what is meant by less than or equal to. That would be underneath the line represented by the equation. Greater than or equal to would represent a feasible region above the line. And yeah, hopefully that helps you out, and I'll see you in the next video. Hey guys, Mr. T here. This is another video. This one is on additional constraints. So often it's necessary to deal with multiple constraints at the same time when dealing with two variables and the relationship between them. So we're going to continue by considering the example from 2A1 feasible regions video. You might remember the constraint was that the total spend has to be $20, or we eventually started saying that it was less than or equal to $20. So therefore 0.4x, 40 cents per sausage, plus y, $1 per sausage, had to be less than or equal to 20. But what if there were added requirements to ensure a successful barbecue from that example, or let's say there was a minimum order of sausages and steaks from their supplier? So we're going to add some more constraints to this particular problem. For example, using that same example, because this graph was already hard enough to draw, what if Jason and Kate were required to buy at least 10 sausages and at least 6 steaks? This results in 2 more constraints to what we had before. X, which is the number of sausages, has to be greater than, and because we're saying at least, it can be 10 or more. So greater than or equal to 10. It's not just going to be greater than, because 10 is acceptable. That's the least that we can have. Now Y, at least 6 steaks. So once again, it's greater than or equal to, because 6 steaks is acceptable. That's the lowest we can go. So it's greater than or equal to 6. So that totals our constraints to 3 different constraints. We have, and I'll try to draw them in green. So overall our constraints now are the one carrying on from before, 0.4x plus y is less than, or equal to 20. And now we have x is greater than or equal to 10, and y is greater than or equal to 6. Right now, we do not have those constraints drawn up on the graph, and the whole purpose of this is to show you how to draw them on. So hopefully I'm not going to struggle so much with drawing these straight lines onto this very slippery screen, but I'll do it anyway. X is greater than or equal to 10, so that is a line, and because it's defined by the x coordinate, it must be a vertical line. So it starts at x is equal to 10, and it's a vertical line from there. So the first constraint is this vertical line, like that. That's a x is equal to 10 line, okay? X is greater than or equal to 10 in this direction, and x is less than or equal to 10 in the left direction. So that's our first constraint drawn on. Y is greater than or equal to 6. So we draw a line at y is equal to 6, and that forms our constraint. So this may be harder because it's a longer line across for me to keep the ruler not sliding around. Fluke that one. So in this case, below this line is y is less than or equal to 6, and above the line is y is greater than or equal to 6. So now our feasible region is more complicated. Obviously, it doesn't start here, because these new constraints are telling us that the number of sausages has to be greater than or equal to 10. So to the right of the x is equal to 10 line, that constraint saying that we need greater than or equal to 10 sausages. And the other constraint is telling us that the feasible region has to be above the y is equal to 6 line, because we need to buy more than 6 or more steaks. But then at the same time, our original constraint was 0.4x plus y is less than or equal to 20. So this diagonal line is the 0.4x plus y line, and it has to be less than 20, so it has to be underneath that diagonal line. Therefore, overall, our feasible region is this smaller triangle within those constraint lines, okay, and following their greater than or equal to or less than or equal to signs, okay. So the feasible region now is a smaller triangle. It doesn't start at the origin. So now all of these results inside are considered feasible solutions, but also the very points on the edges as well are feasible regions. This now has a special name. When the feasible region doesn't start at the origin, it's called a simplex. Does not start at the origin, which is 0, 0. Okay, so now it's called a simplex because it's like enclosed by multiple constraints, and it doesn't start at the origin. And these corners are called vertices. A single one is called a vertex. Vertices, plural. Okay, so if we're talking all of the corners, we're talking vertices. If you're talking about one, it's called a vertex. So any of these whole number points within the feasible region and on the lines forming the boundary and including the vertices are all possible solutions. Okay, so for example, if we looked at this bottom vertex here, that is 10, 6. Is that a possible solution? Well, 10 times by 0.4 is $4. Plus 6 is $10, so that's less than $20. That's fine. That's the cheapest that you could spend, actually. If we look at this solution here, 10, this vertex, sorry, 10, 16. 10 times by 0.4 is $4, plus 16 is 20, so that's spending exactly $20 and buying as many steaks as possible, but still meeting the requirement of 10 sausages. And this other vertex here, so you can think of the vertices, as the extremes as well, considering the new constraints. So here we have 35 sausages and 6 steaks. What is 35 times by 0.4? Can't do that in my head, need to use a calculator. 0.4 times by 35. 14. So that's a $14 spend on sausages with 35, plus 6 is 20. So this, considering the constraints, is the most sausages you could buy, 35 of them, while still purchasing the minimum number of steaks. So hopefully that shows you that the vertices, the corners of all of this simplex are feasible solutions as well. So the take home to get is that, I need my blue pen. Feasible region is now called a simplex. Doesn't start at origin. And what else is there to take home from this? All whole number points within simplex. Within simplex, on boundaries, so on the lines, and on corners, they're all feasible solutions. So we have another way of representing all the possible results, a bit more limited now because we have 2 added limitations here. Alright, so hopefully that helps you out with the idea of added constraints. It's getting a bit trickier now. It's time for you to do some exercises where you're looking at different situations and deciding on what the simplex will look like. Alright, I'll see you in the next video.